Good afternoon, my name is Delaney Lynch.
I'm Dalton Humphreys.
And I'm Amanda Brigash.
And today we're going to talk to you about our numerical analysis of freezing through triple layer skin tissue.
This is just a basic overview of what we will be talking about today in our presentation. So, important biomedical applications of analysis involving triple layer skin tissue freezing include cryopreservation and cryosurgery. Cryopreservation is basically where you slowly cool the biological components to preserve them or prevent them from getting damaged, whereas cryosurgery is where you quickly cool the biological components to kill it. So an example of this could be cancer cells. These two applications are instances in which heat transfer with a phase change does occur. Living cells or tissues cannot be preserved by simple cooling because the water to ice phase change can lead to ice crystal formation in the tissue, which can cause cell death. So it's vital to know how the temperature change occurs within the tissue upon freezing. So these are specifications for the project, and they are based on the study by Singh and Kumar. These include transient analysis, triple layer tissue modeling consisting of epidermis, dermis, and subcutaneous fat layers that differ in individual thicknesses, a cryoprobe temperature of negative 196 degrees Celsius, which is applied to the top of the epidermis, a body temperature of 37 degrees Celsius, which is applied to the bottom of the subcutaneous layer, and we use 37 degrees Celsius because it is assumed that is a healthy human. The epidermis has no internal energy generation because it is thin and non-vascularized, and the dermis and subcutaneous layers each have equivalent metabolic energy generation and blood perfusion. The thermal properties are different and constant in the different layers of skin. The thermal properties in frozen and unfrozen region are different and temperature dependent, and the thermal conductivity and specific heat are the same in the frozen state for all layers.
This is our design on ANSYS for our computational modeling, and this in the bright green on the far left is our epidermis layer. Right here in the middle is our dermis, then the bottom is subcutaneous. The epidermis layer is with a thickness of 0.5 millimeters, dermis is 1.5 millimeters, subcutaneous layer is 3 millimeters. This totals out to be 5 millimeters in length. For our mesh, what we did was, since the epidermis is smaller or thinner than the dermis and subcutaneous tissue, the edge sizing applied to the epidermis was 20, and as of course the thickness of the tissue increased through each layer, so did the edge sizing, so that the dermis is 50 and the subcutaneous tissue is 100. This thermal properties table is taken from the Singh and Kumar research paper. We use these variables or these constants to compare our work to the Singh and Kumar's research paper. The only difference is that we did not use latent heat, and then the thickness of the layer of the tissue we changed in our ANSYS modeling. So instead of these, the values would be 0.5 millimeters for the epidermis, 1.5 for the dermis, and 3 millimeters for the subcutaneous fat.
For our setup on ANSYS, we used a transient analysis to show how the temperature distribution changed over time. And then the boundary conditions, as previously mentioned, the top of the epidermis was applied a cryoprobe temperature of negative 196 degrees Celsius, and you can see how we inputted that right there. And the bottom of the subcutaneous was a temperature of 37 degrees Celsius, and that boundary condition was specified right here. And then all the outer walls were considered to be adiabatic. Also, as previously mentioned, the conductivity, density, and specific heat for each individual layer changed as the tissues reached a freezing temperature, which we consider to be 0 degrees Celsius. So to account for this in ANSYS, we created expressions for each of the properties within each of the layers. And this is an example right here of our conductivity expression for the epidermis layer. And this graph shows how it changes from a certain value as it reaches 273 Kelvin. And then after all the expressions were created for each variable within each layer, we created new materials since ANSYS does not previously have any tissue materials already in there. And so we created the epidermis, dermis, and subcutaneous materials, and then inputted the material properties of each with the expressions that we previously created. And then the data given specified that there was no metabolic energy generation or blood perfusion in the epidermis layer, so we didn't have to account for anything there. But the dermis and subcutaneous layers each had a metabolic energy generation of 2,500 watts per meter cubed, as well as a blood perfusion rate of 0.5 kilograms per meter cubed seconds. And this was accounted for by creating expressions, and so we did a total expression of energy generation was equal to the sum of the metabolic energy generation plus the energy of perfusion, and this is the perfusion equation we used, and then the metabolic energy generation there. And we included those under the subdomain for each of those specific layers.
So this is the results of our ANSYS computational model dealing with transient flow. And so as you can see, we're going to start the video. The tissue is all ready to start off with. When the cryoprobe is placed on the epidermis becomes cooled instantly to almost the same temperature. This is due to the fact that the epidermis has no metabolic generation or perfusion. The dermis and subcutaneous tissue, as you can see, they change in some degree, but they stay darker overall. This is due to the metabolic generation and blood perfusion. And at one point, you can see that there is a fluctuation between the cryoprobe's temperature's effects and the metabolic generation, and this is due to the tissue trying to sustain itself. The results of that, instead of a video form, were then put onto a data sheet, and this is there's 4 different plots. One is for 10 seconds of time, 50 seconds of time, 100 seconds of time, and 150 seconds of time. The 10 seconds is and the 150 seconds are the two that are able to be seen. The 50 and 100 seconds plots are very similar to the 150 seconds. The x-axis is set up so that the distance starts off with the epidermis layer and then moves back. The reason the value is negative is because we set the epidermis in the positive xy plane, and then the dermis and subcutaneous tissue was in the negative xy plane. As temperature increases, you see the distance from the epidermis increases, and this is because that the temperature is warmer where there is blood perfusion and metabolic heat generation.
So we did an analytical analysis to try and determine the temperature distribution throughout each layer, which is the epidermis, dermis, and subcutaneous. This was calculated in the unfrozen and frozen state. Our assumptions for this analytical analysis is that it was a steady state, which is different from the computational analysis where we had a transient state. It is one-dimensional, and there's no perfusion, only metabolic energy generation in the dermis and subcutaneous, whereas in the computational analysis, we did have perfusion. And we also had constant properties, which are the conductivity, density, and specific heat. These are our governing equations that we use to determine the temperature distribution. And as previously stated, the epidermis doesn't have any energy generation, which is why we don't have the energy generation in this equation. So from the governing equations, we determined that these were our 6 boundary condition equations, and we put those into a matrix on MATLAB, and MATLAB calculated these constants for us. In the frozen, you can see that the constants are all similar, actually all the exact same, and that is due to the fact that the conductivity is the same throughout each layer in the frozen state, but in the unfrozen state it is different, which is why all the constants are different in the unfrozen state.
These are our analytical results. So this is for the frozen conductivity variables, and as you can see, those are our equations right over there for the epidermis, dermis, and subcutaneous, and those are our temperature distribution equations. And the temperature distribution, as you can see by this graph, is linear in the frozen state, and the slope is the same throughout, since the conductivity is equivalent in all layers in the frozen state. And then for the unfrozen conductivity variables, again, those are our equations over there using the constants found for the unfrozen conductivities. And the temperature distribution is still linear in the unfrozen state, however, the slopes are different. So as you can see, this is the epidermis layer up until this point, and then as the slope changes, that's the dermis, and then again, the slope changes, and that is the subcutaneous. This is the comparison of both the frozen and unfrozen data. As you can see, the epidermis is the same for both because the conductivity does not affect the temperature distribution for the epidermis since there's no energy generation there. It doesn't have an effect on the equation. However, it does affect the dermis and subcutaneous layer, and since the conductivity is less in the unfrozen state, it accounts for a lesser slope, as you can see there.
So the data from our study differs from Singh and Kumar. This can be accounted for by the fact that they used non-Fourier heat conduction, whereas we did use Fourier heat conduction. And by them using the non-Fourier heat conduction, they could allow for a tissue relaxation time, and this allows the accumulation of enough energy to transfer to the nearest element. Their data was also collected over a longer period of time. However, the overall trend in the temperature distribution is similar despite these mathematical differences in the models used. This is their study distribution, and theirs is set up in degrees Celsius, and this is our study distribution, and it is set up in degrees Kelvin. So this is a comparison of our computational versus analytical analysis. Since the analytical analysis was assumed to be steady state and not have blood perfusion, it is, as you can see, drastically different from the computational analysis, which was transient state and did have perfusion. So it's difficult to make accurate comparisons. And the graph clearly shows how certain assumptions can have great effect on the temperature distributions within the tissue.
So to summarize our analysis and research, we found that freezing through the triple layer skin tissue proved effective for showing how temperature distribution changes upon different conditions and assumptions. The comparisons to Singh and Kumar study show that the use of the non-Fourier heat conduction, as previously stated by Amanda, can lead to different results, or how the cryoprobe temperature affects the tissues. The comparisons between our computational and analytical solutions shows the difference between steady state and transient analysis. This also shows the difference between blood perfusion being assumed and then taking the blood perfusion out of when we do the hand calculations, which simplifies our analytical solutions, but does give us a drastically different graph, and it's linear instead of the other. However, this leads, and thank you, references, I said everything. These are our references that we did use. These are our main references anyways. Is there any questions? Please leave them in the comments below.